Hello everyone, I'm Berkay Yetişer. I'm at University. My mentee Ayça Tekinay is going to tell you about basic topological properties of some of the classical matrix groups and their basic topological properties such as compactness, connectedness, fundamental groups. For example, of special unitary, special orthogonal, symplectic group, etc. Ayça is a last year mathematics student at Boğaziçi University, and thanks everyone for this program. So here's Ayça's presentation.
Hello. Benim. Hello. Today I will talk about the fundamental groups of classical matrix groups. And actually, firstly, I will talk about the Lie groups and their topological properties. They are quite important because they give us a nice idea about symmetry, and they're used often in different areas. Our classical matrix groups are the special orthogonal group, the special unitary group, and the symplectic group. Also, we will continue with the definition of homotopy, and together with the homotopy classes and concatenation operation, we will construct the fundamental groups. Then to find the fundamental groups of these certain groups, we will use the fiber bundle constructions and the long exhaust sequences. The part one of our classical matrix groups are GLNK, SLNK, the orthogonal group, and the special orthogonal group. And the topological properties we will use later. First, GLNR is open, unbounded, and disconnected. The proof is followed by the complement of GLNR. GLNR is closed by the continuity of determinant, and therefore GLNR should be open. And unboundedness follows from the unboundedness of R. Also, disconnectedness follows from the fact that determinant from GLNR to R minus 0, and because determinant function is continuous, and since R minus 0 is disconnected, GLNR should be also disconnected. And the groups ON and SON are compact, and also the proof of this is followed by the identity of the matrices in the orthogonal group, and this implies that every matrix is inside the unit ball of Rn squared. Therefore, ON is bounded. We also have that ON. We also have that function. We can construct this function, and it is a continuous function as Fm equals to M transpose M, which proves that ON is closed, hence ON is compact, and the SON, the proof of SON is also similar like that, and because of the continuity of determinant. These are the other topological properties. ON is not connected, whereas SON is path connected. ON has precisely two path components, and SLNR is closed, path connected, and is not compact for n equal or greater than 2. We will not prove them. They have a little bit long proofs, so we will accept that from now. So the part 2 of our groups are unitary group, special unitary group, and symplectic group. And the topological properties are similar. GLNC is open, unbounded, and disconnected. And also UN and SUN are compact and path connected. The proofs follow from, the proofs are really similar to the first part. So We will not cover these. And also GLNC is path connected, CLNC is closed path connected, and is not compact for n equal or greater than 2. Now we can define the homotopy. The formal definition of homotopy is like that. A homotopy of paths in X is a family of FT, where FT is a family of continuous maps from I to X. And the properties are like that, but the intuition is like from gamma sub 0 to gamma sub 1, you can continuously deform this from one into other, so they are homotopic. Now we will, and from now on we will call them loops, because we will use them as the starting points and ending points are at the same point, so they are loops. They are called loops. And also loops with base points, we will call them base loops. So with the homotopic, not now, but the concatenation operation, with the concatenation operation, we have two base loops, and we are defining these operation, and it is like from a starting point, you're going to half of the way, half of the time, with one loop, and then you will continue with the other loop. Here, they look like they have different endpoints, but you can think it as a T0 and T1 are at the same point, so it is a loop. And two base loops, L1 and L2, are homotopic if one can continuously deform into another, and it's the definition of homotopy. And a base loop is null homotopic if it is homotopic to a constant loop. And if all loops in X are null homotopic, then X is simply connected. And it is also an important property we will use. And the set of all loops that are homotopic to L is the homotopy class of a loop. Now we have the homotopy classes and the concatenation operation, so we're good to define the fundamental group. The set of all homotopy classes under the concatenation operation as a group operation, they will give us a group structure, which is the fundamental group. And the identity in pi x is the constant loop L0. And if X is path connected, the group pi sub 1x is the same for the isomorphic group. So it is up to isomorphism and independent from the base point. And a space X is simply connected if there is a unique homotopy class of paths connecting any 2 points in X. Now we will cover some of the properties we will use. Pi sub 1 of S1 is isomorphic to Z. The proof is followed by the covering maps, homotopy lifting and path lifting properties, but they are really long to prove. So, but the intuition behind it is, I think, understandable. You can think like you're traveling along a circle, and then one loop plus two loops, or inverse minus one loop minus two loop, and it's like the group structure of Z with addition. So they're isomorphic, and also we will use pi sub 1 of Sn is trivial if n is equal or greater than 2. And the last one is for a D-sphere, pi sub k of Sd is trivial if k is less than d. And the sketch of the proof of this is the image of a continuous function from Sk to Sd will not cover all Sd. So the sphere with a point removed, the point we cannot cover, is giving us a structure like this, so we can shrink it to a point, so it is trivial. And also the fundamental group is pi sub 1, but when it is pi sub 2, pi sub 3, or other, etc., they are called homotopy groups, second homotopy group, third homotopy group. They are not fundamental groups. So our last definition here is the fiber bundle. The definition is a little bit overwhelming, but I think with the examples, it's okay. Suppose that B and F are Hausdorff topological spaces, and a fiber bundle with base B and fiber F is a Hausdorff topological space X. All of them together with a continuous map, a projection map from X to B, is a fiber bundle with these two properties. For each B in B, the preimage of B in X is homomorphic to F. And also for every B in B, there is a neighborhood U of B such that preimage of U is homomorphic to U times F in such a way that the projection map is simply projecting onto the first vector. If we come to the examples, they are more fun. For the trivial fiber bundle, you can think like a cylinder as your total space and a circle as your base space, and lines as fibers. It looks like this, and the projection map onto the base, and it looks like the spaghetti with spaghettis as fibers. Also, Mobius strip with the circle as the base space is a non-trivial example of fiber bundles. So now we define the fundamental groups and fiber bundles. So we can use this theorem. It says, suppose that X is a fiber bundle with base B and fiber F. And if pi sub 1b and pi sub 2b are trivial, pi sub 1x is isomorphic to pi sub 1f. And the proof follows by the long exact sequences. In long exact sequences, each map, you can see it here, each map is a homomorphism, and the image of each map is the kernel of the next map. And here, since our first and last one are trivial, when we think about the middle map, let's call it F, the kernel of F is zero, so it's an injective map, and the image of F, since pi 1 of B is trivial, it is surjective because the image is everything, so it is surjective. With the injective and surjective properties, we will have a bijection. So the middle part is an isomorphism. And this proposition says that consider the map P from SON to Sn-1 given like this, with En, the vector with all entries are 0, just the last one is 1. Then with these things, we have SON with P, projection map, is a fiber bundle with a base Sn-1 and the fiber SON-1. We will use this proposition also to find the fundamental groups, and we will also use the equivalence relation, see homomorphisms here, which says a U1 is homomorphic to S1, SU2 is homomorphic to S3, SO2 is homomorphic to S1, SO3 is homomorphic to RP3, and lastly, SP1 is equal to SU2. We will not prove them, but we will use them directly in our proofs in fundamental groups. So if we come to the fundamental groups of a group of SON, for all n is equal or greater than 3, SON is isomorphic to Z over 2. Meanwhile, pi 1 of SO2 is Z. Firstly, we can assume n is equal or greater than 4, then n minus 1 is equal or greater than 3. Since we already know that pi sub k of SD is trivial when k is less than d, we can say that pi 1 Sn minus 1, pi 2 Sn, and pi 2 Sn minus 1 are trivial since n minus 1 is greater than both of them. And with the previous proposition and the theorem, we can construct the long exact sequence again, the same sequence as before, but with fundamental groups. And here, when we have this long exact sequence, still the first one and the last one are trivial. So the middle part should be an isomorphism. Therefore, that means pi 1 SON is isomorphic to pi 1 SO3 for all n greater than 3. So the rest follows from the fact that SO3 is homomorphic to a real projective plane. since SO2 is homomorphic to S1, pi1 SO2 is isomorphic to Z. Yeah, and since the fundamental group of RP3 is Z over 2, we will have the proposition for all n equal or greater than 3, fundamental group of SON is isomorphic to Z over 2. And for these propositions, we will use the same steps with long exact sequences and fiber bundles, etc. Just the difference between these and the previous one is that it says the group SUN is simply connected for all n equal or greater than 2, because SUN, the fundamental group of SUN, gives us trivial after 2. So it is trivial after 2. It should be simply connected, as we said before at the beginning of the presentation. And for all n greater than 1, we have this. Also, we also said that with the equivalence relations and homomorphisms. And the last one is the same, but SPN gives the trivial fundamental group n is equal or greater than 1 for all n greater than 1. So that's all for my topic, and these are my references. Thank you for listening. Do you have any questions?